Suppose you've gone to the Red Sox game. The batter is ready to hit the ball and is going to go for a home run. If this is going to be happening at Fenway Park, you're going to have quite the obstacle, namely the back here behind the outfield known as the Green Monster. This is a rather tall structure. It's over 37 feet tall, or if we're going to use good metric units, it's going to have a height of about 11.33 meters. Our batter here, right there at home plate, is going to be approximately 95 meters away from that board. So if the batter really wants to get a home run, he's going to have to make sure the ball goes far enough and high enough to get over the said Green Monster. So we can imagine the pitch comes in, bam, it hits, and it's going to then have some velocity vector, and it'll fly off at some angle. So let's try and see if in a particular case the ball can actually get over. Let's suppose that the velocity of that ball initially is a mere 35 meters per second. And let's say that the angle that the ball leaves the bat is going to come off as 30 degrees above the horizontal. So in this case, the horizontal along the x direction here. And we want to now figure out, okay, hitting the ball with that speed at that angle, does it actually succeed in going over the Green Monster? There's in fact more than one way to see what's going to happen. So we'll try two different methods. First one, though, we'll consider where is the ball going to be once it's actually covered that distance of 95 meters. So if we were to say looking at the displacement in the x direction, and we can express that with the kinematic equation like so. And since this is going to be along the x dimension, there's no acceleration there. We're assuming no air resistance, so we can just ignore that term. And the displacement, x minus x naught, should be 95 meters. All right, so we just need to figure out, all right, what is v naught? V naught x, I should say, that component. Well, if we were to draw out our velocity vector here, this is v naught, this will be v naught x, this is v naught y, and we are given this angle here, the one relative to the horizontal, as 30 degrees. So we can see that, all right, if I want to get v naught, I could use the trig function cosine of theta, which will be equal to adjacent, in this case v naught x, divided by hypotenuse v naught, and with one step of algebra, we'll see that v naught is just equal to initial velocity vector times cosine, in this case of 30 degrees. And if we plug our value in for v naught, which was 35 meters per second, plug in 30 degrees into cosine, and we find that we'll get a velocity of 30.3 meters per second. All right, so we can now use that information and plug it into our kinematic equation here and try to solve for time. So let's make ourselves a little bit of space. So we're going to have our x minus x naught equal to v naught x times time. So t equals our displacement divided by our velocity in the x direction. That's 95 divided by 30.3. And with that, we get 3.13 11.3 seconds. Now, why was this so important to us? Well, now we know basically how long it's going to take the ball to get from home plate to the green monster. We can now figure out, okay, in that time, what altitude does the ball have? Is it above the green monster, below it? Is it even underground, in which case it's now been bouncing on the ground? Let's take a look at that. So again, let's make ourselves a little bit of space. Set this over here and keep our time. So if we want to then look at the y displacement, y minus y naught equals v naught yt plus 1/2 a yt squared. We know that the velocity in the y direction, is going to follow the same sort of trigonometry that we did here, but in this case then we're going to be relating it not with cosine, but with sine, and using the same logic. So we'll find that v naught y is equal to v naught times sine of 30 degrees, sine of that theta. And so we'll find that that velocity is going to be 17.5 meters per second. The acceleration due to gravity will be negative 9.8 meters per second squared, and time is the value of time that we found here that we're just going to plug in. And so we just go ahead, plug and chug, and we see what that new height is, and we discover that height it comes down to is 6.77 meters, and that is below the height of 11.33 meters for the height of the monster. So this value means we do not actually get a home run. The ball is basically going to bounce off the green monster about a little more than halfway up. So it'll look close, and then bounce. Maybe the player will still get lucky and be able to catch a few bases. If the outfield isn't doing well, then perhaps even a home run can happen, even if it doesn't leave the field. But nonetheless, nobody's catching that ball in the stands. So this was basically starting from information in the x direction and figuring out how long it would take the ball to travel from home plate to the end of the outfield. Let's now try a reverse way and see what we could do if we started from the y position. So let's start with the displacement equation for y. So what we know is we are ultimately wanting to figure out, okay, we could use this same equation and try to figure out what time it is when the ball is at the height of the green monster. If we do that, we can see, okay, when the ball is at this height, how far is it along the infield, or is it even beyond the infield? We can do that by figuring out what this time is when it's at a height of 11.3 meters, and see if that's, in that amount of time, looking in the x direction, how far the ball has gone if it's less than or greater than 95 meters. So, our y displacement, y minus y naught, we're going to look at when it's at the height of the green monster itself. V naught y is the same value that we found before of 17.5 meters per second, and acceleration due to gravity is negative 9.8 meters per second squared. So we just want to solve for time, and this means we're going to be solving a quadratic equation, so we'll get in the form of the quadratic equation. So we'll have 0 equals negative y minus y naught plus v naught yt plus 1/2 at squared. So that's going to be negative 11.33 plus 17.5 times time minus 4.9 t squared to put in all of our numbers. And so this is in the form of the quadratic equation, and so we'll have to solve for that using time, and we're going to get two different time roots, which ultimately kind of makes sense because there's going to be two times that the ball could potentially have that height of 11.33 meters on the way up and on the way down. If it never, of course, pops out high enough to even go to 11.33 meters, then, well, it would never leave the field at all, no matter how many times it happens to bounce off the ground or anything like that. So we need to solve this equation using the quadratic equation, and when we do that, we find the time is, times will be 0.850 seconds, and the other time will be 2.72 seconds. So like I say, the first value here is basically when the ball is still moving upward and how far it is. And in this case, this is when the ball is moving downward. Now, after this time, the ball is only going to be below the green monster. So this is the time we should look at and see, does it actually go far enough in that time? Will it have enough displacement in the x direction that it is beyond the green monster? So how do we figure that out? Well, we can take that same time and plug it into the displacement equation for the x dimension. So we'll make ourselves a little bit of space to do that. So x minus x naught equaling v naught xt plus the acceleration term, which is just going to be 0. Time, we know. The velocity in the x direction we solved before as 30.3 meters per second. So it's just a matter of plugging in 30.3 into the velocity, 2.72 into time, and we see what displacement that is, and see is that beyond the green monster, which was supposed to be 95 meters away from the plate. So if we do that, we will find that, as expected, it doesn't go quite far enough. We find a displacement of 82.4 meters, which is not even to the green monster. So at that point, it's going to start going below the height of the green monster, and when it finally reaches there, it will be hitting the backboard, pretty much as we saw before. So this is two different ways of doing the same sort of problem and just comparing them and getting similar results, both telling us that, indeed, this batter needs to either choose a different angle or hit the ball with a greater velocity.